is Everton de Matos. I work for TII. And this talk is about a TE, a seL4-based TE for RISC-V. It's basically a follow-up of a talk from last year. So last year represented kind of the definitions, architecture of this work that we have been done. And now we have some results, some performance evaluation that we did on the PolarFire platform. So basically, just some introduction, motivation, that we have lack of security in a lot of devices, and TEs appear as a possible solution, or one of the possible solutions to have a better security in some of the scenarios. And from our investigation, we saw seL4 as a nice option as a secure OS for our TE. So basically, this is what we done. Just some definition concept slide as well about TEs. Basically, TEs are those secure execution environments, so we can run secure code, cryptographic operations, any other use case. And basically, we have those definitions of a normal OS, non-secure word in one of the sides. Sometimes it appears also as a rich execution environment, REE. And the other side, on the right side of this figure, we have the TE. That will be our trusted environment with trusted application, trusted kernel, all the trusted in one of the sides. So it should be isolated from the normal OS or the non-secure world. In this, there are technologies in different architectures that can enable such kind of environment. So some of the use cases that we can have on TE, also for some of the tests that we made about secure storage, execution of code in a secure way or like an isolated way, some cryptographic or crypto operations that we did some testing in this way as well, remote attestation, secure multi-part computation. This is just to show some of the examples of use case that we can have with a TE. And some nice work that already have been done on seL4 with TEs. So I recommend these two papers. I think they are very nice. And basically, there are some approaches that already use seL4 as a secure OS. In those two cases, it's on ARM architecture, so both of them. The first one, the one here in the right side of the slide, they used some kind of ARM trust zone concepts with seL4 to create their TE. But anyways, just like some related work, just for you to be aware that seL4 has already been used as a TE, apart from the work that we have been done. On the RISC-V as well, because those two examples was on ARM, but on RISC-V, TEs on RISC-V, we already have a lot of examples, people working on these scenarios. We have the Penglai and the Keystone as some examples of enclave-based TEs on RISC-V. And Keystone also, they provided some example scenarios, not that they published work or experimentations on these scenarios, but they said that it's possible to use seL4 as a TE on RISC-V, either on S mode, supervisor mode, or in machine mode, but just also to present some of the related work on RISC-V this time. This is also very interesting. This is from the RISC-V community. They have this AP-TE, this RISC-V application processor TE, that is a task group from the RISC-V community. They define some of the specifications for TEs on RISC-V. And this is something that I already presented last year, but it evolves from last year to this year. They are like having constant meetings and discussions on how to define the standard for a TE on RISC-V, because on ARM we have trust zone, on x86 we have SGX, for example, and for RISC-V there is the APTE or the CoV architecture, that is the confidential computing architecture that they are defining. Basically, they define these TE virtual machines, the TVMs, you can see in the TE side over there. And the TSM, that is this TE security manager, that is the TE itself, that SL4 would be placed on that space. But you can see that in this scenario, they put in the HS mode, that is the hypervisor extension mode on RISC-V. And unfortunately, we don't have any, or like just very basic hardware on this side, and not like commercially available hardware with this kind of hypervisor extension. So this is some standard to be adopted. But in our case, we put SL4 on the supervisor mode, so it's a bit different, but just for you to be aware of this kind of standard that will come up to the RISC-V community very soon. So our approach. We deployed our solution on a PolarFire platform that has 4 application cores, 1 monitor core. And then we have, what we did was to put on the non-secure world, on the rich execution environment, the REE, on the purple side, the Linux operation system, and on the other side, we have SL4 as the TE operation system. You can see that we put 3 cores for the Linux and 1 of the cores for the SL4, so we did this kind of distribution. And we have, of course, the monitor core just for the HSS bootloader. So this is the whole architecture that we have. Basically, we have 3 ChemKeys applications. You can see on the green part of the figure. The REE COM, or the Rich Execution Environment Communication, is just basically to establish this communication between the secure world and the non-secure world. We use RP message as a standard for this kind of communication. We have, of course, some of the TE services. We follow the standard of OpenTE for this implementation. And then, as example, we have PKCS11 enabled, some other crypto operations, and security storage as well. And on the right side, we have the system controller just to use the PolarFire hardware enabling, or the PolarFire controllers. On the Linux side, we developed this kind of SL4 tool. It was just a tool for us to test our system, to call the TE services from the other side, from the secure side. So this tool, we can call any of our TE services, and we also, as I mentioned, we use RP message for this communication. And then, of course, we have the Linux here on the side, so this is basically the building blocks of our architecture. Then, for the evaluation, what we did as evaluation was to do 2 kind of tests, 2 string of tests, I would say. One about the rich execution environment performance, and the other about the TE services. So the idea from the first one, the rich execution environment performance, was to access the performance of the Linux itself while we have SL4 running in the 4th core as a TE. And for the other kind of tests, for the TE services test, basically we evaluate in terms of latency, performance itself of some of the TE services, so crypto operations, random number generation, signing, all those kind of operations that a normal TE have. And basically, as I mentioned, we use the PolarFire as our platform for tests. And as we did these tests in the beginning of this year, or the first half of this year, so we used the version 12 of SL4. So, going a bit more in details of the first test that we did in the Linux side. So basically we defined 3 scenarios just for us to compare. The idea was to know if the SL4 running in one of the cores would affect the Linux performance on the other 3 cores. So of course in the PolarFire we have PMP enabled, so it should not affect the performance, but even so we just did this test just to confirm this hypothesis. And for this we had these 3 scenarios to compare. The scenario A, or the first scenario, is the one that I presented you in the figure, with Linux running in 3 cores and SL4 running in the 4th core. For the scenario B, we have also Linux running on the 3 cores and the 1 idle core, so no seL4, nothing running in the 4th core. And for the scenario C, we have the Linux running on the 4 cores and also with no seL4 This was just like to kind of compare. We did a bunch of CPU and memory load, I/O load as well, network load as well, just to see how the Linux would behave. And basically, for no surprise from our side, there was no much impact or practically zero impact of having one core with seL4 or one idle core, because we have PMP for this separation, but just for us to like be sure and just to confirm this hypothesis, we did this kind of tests. You can see that there was some variance on the network throughput, but this can be can be just due to the network oscillation, not like major, not related to our implementation itself. And then for the TE services, we did some evaluation on the crypto services, on the TE services themselves. The first one was the random number generation from PKCS11 as well. And in this graph, you can see the latencies for generate this amount of random numbers, and it's in bytes. So usually crypto services to generate a key or something doesn't use much more than 128 bytes or even less most of the cases. So we can see that it was pretty stable, our performance until that point. Of course, afterwards it increases a bit, but is from limitations of the hardware itself. So just like to make sure that our service was properly generating random numbers. And then we did some tests on the key pair generation and then encryption and decryption with those generated keys. For the first one, for the key pair generation in 3 different sizes for the RSA algorithm, and then we have like those results. I have a table on the next slide that will print those results in more details. And for the encryption and decryption, also after generating the key, we did a bunch of tests for encrypt and decrypt files, and you can see that for the encryption, they are pretty much stable, the results. For decryption, it varies a bit depending on the size of the key, which is normal. Here in this table is the same results as before, but plus the signing and some more information about the test that we did with the average in the first line or the mean in the first line. But we have like, the next slide I can show you, we have like some publication that you can see in more detail instead of looking to all the numbers now. I let you with the reference. The first one, the first publication, it's already available. The second one is in the second batch of reviews now, so hopefully should be available soon. And also, you can check out our implementation. You can start by the manifest, but of course, over there you can see all of the other repositories, and you can go ahead and test in your PolarFire. And if you face any issues or find any problem, feel free to fix it for me, or or you can drop me a message, drop me an email. I can help you through any issues that you may find. So that's it that I have to you. Thank you.
Hello, thank you for the talk. I just want to confirm kind of like understanding of the work. So you were not very happy with existing TE architectures maybe, and you were willing to explore basically different architecture with core separation and having dedicated core for dedicated world. What I've found interesting is actually doing comparison with other architectures instead of just different parametrics within your architecture. Are you planning to do any more exploration in this space, or yeah, that's the question.
Okay, thank you. The thing is that on the RISC-V world, there was no previous implementation of TE using seL4, so that's why we went through this scenario. So there was TEs on seL4 on ARM, for example, but not for RISC-V, and then we find that it would be a nice work to do. And in terms of comparison, it's a bit, hard to compare with other works as we don't have something like very similar available. But yeah, we are planning to do some comparison with the enclave modes, but the Keystone, Penglide, they are enclaves, not like, it's not exactly the same, but we are planning to do some comparison even so to have some more results in that regard.